Good morning. My name is Jim Fawcett. This is the second in a short sequence of videos about the Rust programming language. In this sequence, we're focusing on models, that is, the major ideas that go to make up the Rust programming environment. So in the last video, we introduced Rust and demonstrated a little bit about how the Rust build system works, and we use Visual Studio Code to view things. In this sequence, we're going to look at a sequence of slides that are all devoted to the Rust ownership model. So this is a video about Rust ownership. We left off last time with a slide that described the safe type system for Rust. Rust is a type-safe language, avoids undefined behavior because of its language constructs. Its type system prevents not only undefined behavior in a single-threaded program, but prevents data races in multi-threaded programs, surprisingly, again, with just a single ownership model. And so basically the ownership model prevents mutation combined with aliasing. We're going to explain that a little more in just a minute or two. And it prevents mutation aliasing and lack of access ordering, that is making access sequential in multi-threaded programs. Now, in this sequence, we're not going to talk about multi-threaded programs. Eventually, I'll add a video or two about the threading model and the way it works and some projects that use threading, but not in this sequence. Okay, so let's talk about ownership. So the ownership rules are really fairly simple in concept. The Rust ownership policy is a reader-writer lock. Any number of readers can view a value in the Rust system, can view a value. But if there is a writer, one and only one writer, and no readers can view that data. So we can have a single writer, or we can have multiple readers. Now, readers are divided up into a couple of categories, and that's what we're going to get to next. So any number of readers may access the values simultaneously. Writers get exclusive access. No other readers or writers. So what are these readers and writers? Any variable bound to a value with no mute qualifier is a reader. We're going to talk about mute a lot, so just hang in there. So the original owner, says let s equal string from a string. It's just syntax for creating a string object from a literal string. And s is the owner of that string. Now, I can make a reference to that value, let r equals a reference to s. And so now s was a reader. It doesn't say mute, so it's a reader. Once it's constructed the string, obviously it had to be able to construct it. But once the string is constructed, then s isn't allowed to change it because it doesn't have a mute attribute, where mute stands for mutable. And it really means exclusive access in a sense. That's what mute means. References to the data. So here I created a reference, and this reference is a reader because it doesn't have the mute attribute either. So there's two readers. Okay, I can have any number of readers at the same time. Now, any variable bound to a value with a mute qualifier is a writer. The original owner let mute s equal string from another string. Now this guy is a writer because s is mutable, And I can create a mutable reference to that string, let mut R equals reference to S. So I've got two different writers, and I can only one is allowed to get access to that data. So here we're getting into the ownership story. The idea is simple, but there's some details to take care of. So that's where we're going. So you might notice that by default, Rust variables are immutable, unchangeable. You have to opt in to changeability. And that's a good thing. Okay, now there's another thing we need to think a little bit about, and that's copying and moving. If a value, all its bits are contained in one contiguous block of memory, it's blittable, meaning that we could do a mem copy, just a raw copy of those bytes someplace else, and wind up with a valid object. So if the data resides in one contiguous block of memory, then it's copyable. And we say it has a copy attribute. And so here, let x equal 3.5, that's a floating point number, that's splittable. So I can make a copy. Let y equals x makes a copy of that value. So I've got two variables, but they're not bound to the same value. They're not bound to the same location, okay? Because what happened here is we made a copy. Y equals x makes a copy of the value of x into a new storage location, into y storage location, okay? So I now have two variables bound to two different values that happen to have the same bit sequence. There's, two different locations that have the same value. Okay, so y gets a copy of x's value, two separate locations. Copy binding creates a new owner of new data. Now let's talk about a move. Data resides in two or more blocks, usually one in the stack, one in the heap, like a string. So here, when I say let S string from a string, I get a string object in the stack frame. And that string object has a pointer to an array of characters, a buffer of characters on the heap. And it has a length measure, an integer, and it has a capacity integer. So a string in general, it still works just like a vector. It really is implemented underneath just like a vector. A string has a given number of characters, but it probably has a capacity that's larger than that number of characters. And if I wanted to add a new character, I wouldn't reallocate memory. But when I filled up that memory buffer, okay, and I add a new character to the string, concatenate it to the end of the string or something, then the string will silently go away and allocate new memory, okay, and point to that new memory. Okay, now, so here's what a move does. Data resides in these two contiguous blocks. Now when I say let t equals x, I didn't copy it, I moved it because this is blittable. Rust won't copy blittable data, ever, okay? When I say copy, I'm talking about a copy trait. And what happens here is when you do this kind of a binding, it looks like an assignment, but I'm really, it's a binding, okay? I'm copy constructing Y, if you will, okay? And here, I am move constructing T, for those of you that are familiar with C++. That's really what's happening. So what's happened is, and I'll have a diagram on the next slide that shows how that happens a little more. But basically, what happens is that T takes ownership of S's data, and now S becomes invalid. I can't use S anymore. Okay, so what I've done is transfer ownership. This statement has transferred ownership of the string array on the heap from S to T and invalidated S because S no longer binds to that memory on the heap. So S value moves to T, S becomes invalid. Move binding transfers ownership. Copy binding creates a new owner of new data. Move binding transfers ownership. Copy happens when the data is blittable. Move happens when the data is not blittable. I can't do with a single mem copy. I can't copy a string because there's two hunks of it. Part of it on the stack, I can blit that, and part on the heap, I can blit that, but I can't do one blit and copy it. Okay, so now here's the picture. When I do a move, here I had the string S. It has a pointer to the A string on the heap. It has a length and it has a capacity. And now when I say let T equals X, what I've done is I've blitted this block down here. Nothing has changed. So this guy still points up here. And now we mark this guy as invalid. Okay. He no longer can access that data. Nothing we could do could make him access that data. Okay. So we've transferred ownership, and it's very fast. We didn't copy any characters around it. They just sat here on the heap wherever they were, and we blitted this control block, is what I call it, the string control block. We blitted it to T's location, and now T has ownership. So Rust will copy any value contained in a single contiguous block. X equals 2, that's an integer, it's an I32, and so it's copyable. Satisfies a copy trait, and when we bind Y to X, we just make a copy. So we have two separate memory locations now, the X and Y memory locations, and they both happen to have the same value 2, but they're in two different memory locations. So they're, if you will, two different values with the same bit sequence. Any value requiring separate parts, like the string showed in the right panel, will be moved, just like we said. Okay, now we're ready to dig into the ownership model. Whoops. Yeah, I explained all this before I got to the slides, so we can just skip over this. So, you know, the slides are available. There's a link on the front page of this. If you go to the first video, you'll see a link to these slides. You can go grab it. So, okay. So there's one other thing before we dig into the ownership model in detail. There's one other thing that we can do. So for these non-blittable types, we can define a clone method. I won't say you could do it for any non-blittable type. For most non-blittable types, you can create a clone method. And the way that works is you say let T equals S.clone. Now, we didn't move S, we cloned it. So that means that we copied the characters. So the clone operation didn't blit this down to here, okay? What it did was it blitted this string to a new location in the heap, okay? And then it just set up this to point to that new location. So S clone, so it's still valid. T string now owns a copy of the character resource that S holds. Okay. The clone is always called explicitly. Copies for the primitive types are called implicitly. You saw me do that right here. Right here, you see me. This is an implicit copy. I didn't. I just did a binding to that data, and the copy happened implicitly. But that never happens. The clone is never implicitly executed. You always, the using code has to ask for the clone. And Rust does that because it's an expensive method, and Rust wants you to know when you're doing expensive things, okay? Because its main goal is to be a system programming language, and for that, it has to be fast. So, okay. So that's copy, move, and clone. And by the way, the string class has a clone method, and the vector class has a clone method, and so on. And for your own types, you can create clone methods. You'll see me do that in a later video. Okay, so now let's get back to read-write locking. So references and read-write locking. A non-mutable vector and references, I can have any number of references to that non-mutable vector. Vector, you know, it could be a string. It's just an example of a non-blittable data structure. You know, vector, this character data is held on the heap, and the vector has a control block that looks just like the string control block in the stack frame. So it's very like a string. And so it's not blittable. Here I can create an open-ended arbitrary number of references. I'm creating non-mutable references. I can have an arbitrary number of non-mutable references. This is the simplest case. Now, if the vector is declared to be mutable, I can v can change its own value. I can still have an arbitrary finite number of non-mutable references. These are called borrows. But once I've created this reference, v cannot mutate. Because remember my C++ example, I had a reference and I mutated the vector and it went off and reallocated memory and left me with a dangling reference. So Rust isn't going to let us do that. So once we've done these, created these references, so we're essentially borrowing V's ability. If these were mutable, we'd be borrowing their ability to mutate. But you know, so the Rust developers call this a borrow. So V can't mutate until these references go out of scope or they're dropped. We can drop them. I can just say drop R1, and that has the same effect. So if I dropped R1 and dropped R2, then I could mutate the vector V. But until I do, or until they go out of scope, then I can't. A very common scenario, the most, you know, I'm going to illustrate creating all these references all over the place. So we normally don't do that. Most of the time, we're using references for pass by reference into functions. And when we do that, it's all quite simple, at least as far as the user of the function is concerned, because the references get borrowed, but the thread of execution is inside the thread, and when the function returns, those references go out of scope, and so the whatever was passed in can be mutated. All right, so here's the most complex situation. We have a mutable data vector and a mutable reference, and we can only have one mutable reference. We can't ever have more than one mutable reference. And if we have a mutable reference, we can't have any non-mutable references. Remember, the non-mutable references are readers. This mutable reference is a writer, and this vector is a writer. Now, while I can create them, I can't mutate it. You know, this guy borrows V's ability to mutate. So V can't write while R is, before R goes out of scope. So we only have one writer, R. When R goes out of scope, now V can write again. That's the essence of the model. So here's a view in Visual Studio Code. If you remember from the first video, if you don't, you might stop this video and go take a quick peek at my C++ code. This is Rust code that's trying to do the same thing that C++ code did. Now, you'll notice here, I have a vector V, okay? I set its capacity to 3. Syntax is a little different than C++, same idea, same thing, instead of saying reserve. And I push back 1, 2, 3, so I filled up its capacity, okay? And now I'm gonna create a reference to V1, just like I did in C++. This won't compile. If I try to mutate with V, the compiler is saying, nope, can't do that. Okay. The compiler does an excellent job of stopping, and it's telling me exactly what the problem is. It says here, V push fails to compile, can't mutate while borrowed. It's showing me where the problem is. Okay, V push 4. Okay. Here at line, it's telling me in line 13, in line 14, I have the address of R1. Here's where I'm using that reference. Okay, this is okay. This compiles just fine because this points to the whatever the address is. That's going to point to that address. Okay, but here R1 is fixed with, you know, this is the old address, so this is just not going to compile. If I can mutate this statement, you know, this won't compile, but the problem really is here. Now, if I remove this statement, this will compile again. In this next one here, I commented out that statement, okay? I have a reference, but I've never used it, and so the compiler will allow me to mutate V, as long as I don't use anywhere in that program. But if I come along and uncomment this, even though it's after V, now all of a sudden, after this push, all of a sudden this will become uncompilable. Okay, cool. And so the Rust compiler, one of the big advantages, one of the best parts of Rust is its compiler. Its compiler does a great job of enforcing this ownership model in a very palatable way. You know, at first, when you first begin writing Rust code, you're going to fumble around a little bit with it and beat your head on the wall. But the error messages are really clear, almost always. You know, you can give it a grievous enough error that it eventually will get confused and stuff. But, you know, almost always the error messages are right on. They point to where the error is and very often will tell you exactly what you have to do to remove the error. They'll give you a suggested solution. So, cool. So, hello ownership. Every value has one and only one owner. Ownership can be transferred with a move. Ownership can be borrowed with a reference. References hold a view into the value. When a reference goes out of scope, nothing is dropped, nothing is released, because that reference doesn't own the value, it borrowed the value. When I drop the original owner, the vector or the string, then those resources are released. So they're freed from the heap memory. But when a reference is dropped, goes out of scope, nothing happens because it doesn't own that data. It's just borrowed a view into that data. So reference hold a view into the data. Original values owner can't mutate while borrowed. Immutable references can be shared. Mutable references are, so this means I can have several references, immutable references pointing to the same memory location, same value. Mutable references are exclusive, only one. Borrowing ends when a reference goes out of scope or is dropped, and typically that happens. Most use of references are for functions that pass by reference. And so as far as the calling code is concerned, it's very simple. I pass in my argument by reference, and I can't do anything until that function returns. You know, it's just like to me, it's a single statement to the caller. It's just a single statement. Function executes. Now I can mutate it again because those references went out of scope. Great, quite straightforward. You know, inside the function, you know, now you start to get into some of the issues we've been looking at. Okay. This fits very well with pass by reference function arguments. Values are by default immutable, but can be made mutable. This is immutable. This is mutable. And, you know, here's a little another quick view. You know, there's some details here. So here I have function main, let x equal 5, let mut y equal 5. Okay. So I have this is just illustrating, let x equal 5. If I uncommented this, here I say x equals 6. If I uncommented it, it would fail to compile because I attempted to mutate a variable that's not mutable. Now let's create a mutable y whose value is 5. And now I'm going to mutate it to 6 just to show that, yeah, I can mutate it without getting a compile failure. Now, inside the scope, I'm going to create some references. So when I leave the scope, then the references go, you know, are dropped. and I can mutate. So once I've left the scope, I can mutate y again. But here, let r equals a reference to a mutable reference to y. So y is mutable, and this says the reference is mutable as well. It means that I can change y through the reference. Now here I say, now unlike C++ references, ry is, in a sense, is like a pointer. And so I dereference it right here. I'm dereferencing. So here's the value. And so I'm adding 1 to that value. And now I am assigning that value to the contents of y. So I'm just adding 1 to the contents of y. Now, if I had y equals y plus 1, this would fail to compile because I have an outstanding borrow. You know, I'm not allowed to mutate while there's a borrow on my value, my own value. So now I can print out the value of y. I'm sorry, I can print out the value of the reference. And again, you know, I can't print y. I can't mutate it, but I can't print y either, because if you looked at the calling sequence here, I'm passing a reference of y into that function, and I already have a mutable reference to y, so I'm not allowed to do that. And the compiler will tell me very nicely, it'll tell me exactly what the problem is and, you know, how to fix it. So now when I leave the scope, this reference goes out of scope, and now I can mutate y and I can print y, and away we go. Okay, that's the essence of the ownership model. And inside functions, we can, you know, we can get into these things. If I call a function that does a borrow, and I've already got an outstanding mutable borrow, that's going to fail to compile. But again, the compiler does a beautiful job of giving us warning. It'll tell us exactly what's going on. Okay, so now let's kind of summarize. Immutable references, I can have any number of immutable references. And so here's immutable S with 2 immutable references. Original owner cannot mutate until all active references are dropped or go out of scope. So I can call drop on R1, drop on R2, then I can mutate. Here's a function show S by reference. So here I'm passing a string by reference. So let mut t equals string from another string, show reference to t, and now I can mutate t because the reference to t has gone out of scope. As soon as I leave that function, that reference goes out of scope, and now I can mutate t. So from a user's perspective, this is simple. You know, just ordinary pass by reference, no big deal. All right. Mutable references. Only one mutable reference may be declared for a value. Okay. Here's a mutable string. Here's a mutable reference. I can only create one. These won't compile, either mutable or unmutable. They won't compile because I already have a mutable reference out. Original owner cannot mutate until the active reference is dropped or goes out of scope. So here's a function. S, I'm passing a string, let mut t equals string from another string, show a t, and now I can push so. Because that, here I created a reference, an immutable reference, but I created a reference, but when I leave show, that reference goes out of scope. That reference to t ends its lifetime, and now I can mutate t with this push string. Just appends a string at the end of t. Okay. So this ownership summary, you know, so this is like a summary of the summary. Let's all be really quick. Simple rules. These simple rules provide for memory safety. X equal Y, copy if blittable, otherwise move, transfer of ownership. Can't use Y if moved from. Let R1 equals reference to X, let R2 reference to X. I'm aliasing here, R1 and R2 are aliased to X. May have any number of immutable references. X may not be mutated while they're active references. Now, mutable Z, R3 equals mutable Z, may only have one mutable reference. References become inactive when they go out of scope or are dropped. I can just call drop on R3, and now once I've called drop on R3, I can mutate Z again, okay? So, so that's it. That's ownership. All right. So we'll pick up with, you know, object models and things like that in the next set of videos. So for now, we'll stop in the interest of brevity, and I'll say goodbye.